Hello everyone, I hope you are doing good. So in this video, we'll be covering about Hidden Markov Model, also called HM. My name is Aditya and let's start. So we'll be covering the introduction first. So a Hidden Markov Model is a statistical model used in various fields, including speech recognition, natural language processing, bioinformatics, and many more. HMM are particularly well suited for problems involving sequences and time series data. The model is named hidden because it involves two interrelated stochastic processes, the observed sequence and an underlying sequence of hidden state. Here are the key components and concepts of a hidden Markov model. Number one, states, hidden state. The HMM consists of a set of hidden states which are not directly observable but affect the observable data. The hidden states form a Markov chain, meaning that the probability of transitioning from one state to another depends only on the current state and not on the previous state. Number two, observation, also called emission probability. Each hidden state emits observable symbols or data with certain probability. These probabilities are represented by the emission probability. In some applications, these are also called emission probability or output probability. Thirdly, the initial state probability. The model also specifies the probability distribution of starting in each hidden state at the beginning of the sequence. The last, state transition probability. HMM defines the probabilities of transitioning from one hidden state to another. These transition probabilities can be represented in a transition matrix. The core principle of an HMM is that it generates a sequence of observable data points by moving between hidden states over time. The sequence of hidden state is not directly observable, it's inferred from the observed data. HMM are used for a variety of tasks, including speech recognition, recognizing spoken words or synonyms from audio signals. They are used for natural language processing, also called NLP, part of speech tagging named entity recognition, and other sequence labeling tasks. Bioinformatics, analyzing biological sequence such as DNA, RNA, and protein sequence for gene finding and sequence alignment. Gesture recognition, recognizing and tracking gestures in computer vision applications. Lastly, finance, modeling financial time series data for application like stock market analysis. Inference in HMMs typically involve two main problems, forward algorithm and Viterbi algorithm. The forward algorithm computing the likelihood of an observing of a given sequence of a data, while the Viterbi algorithm finding the most likely sequence of a hidden state given a sequence of observations. This is useful for task training on HMM, often involves the Baum-Welk algorithm, which uses the expectation maximization, that is the EM algorithm, to estimate the model parameters from a set of training data. Hidden Markov models are powerful tools for modeling and making inferences about sequential data, but they do have limitations such as the Markov assumption that state that only depends on the previous state, which might not always hold in real-world scenarios. Let's take an example. We'll be predicting the weather for the next day based on the current day using the HMF, that is Hidden Markov model. So as you can see, I have written a Python code that imports the NumPy, matplotlib, cbond, and the HMM library. Okay. So here we define the model parameter. So in this example, the state space is defined as a state, which is the list of two possible weather conditions, sunny and rainy. The observation space is defined as observations, which is a list of two possible observations, dry and wet. The number of hidden states and the number of observations are defined as constants. So here we are defining the states sunny, rainy, and then we are finding the length of states. Those are 2. We are printing it. So the number of hidden states, as you can see in the output, is 2. And then according to our observation, there are 2 observations too. The start probabilities, transition probabilities, and emission probabilities are defined as array. The start probabilities represent the probabilities of starting each of the hidden states. The transition probabilities represent the probability of transitioning from one hidden state to another, and the emission probabilities represent the probability of observing each of the outputs given in a hidden state. The initial state distribution is defined as state probability, which is an array of probabilities that represent the probability of the first state being rainy or sunny. The state transition probabilities are defined as transition probabilities, which is a 2 times 2 array representing the probabilities of transition from one state to another. The observation likelihood are defined as emission probability, which is a 2 times 2 array representing the probability of generating each observation from each state. Here we have a code demonstrating the initial state distribution with a probability of 0.6 and 0.4. We are printing the state probability as 0.6 and 0.4. On the right hand side, you can see the outputs of our code. Then we define the state transition probabilities in the 2 times 2 array matrix, and then we are printing them out too. Just like that, we also find the emission probability and print them out too. The HMM model is defined using the HMM category HMM class from the HMM Learn library. An instance of the categorical HMM class is created with the number of hidden states to n hidden states, and the parameters of the model are set. Using the start prob, transmat, and emission prob attribute to the state probabilities, transition probabilities, and emission probabilities respectively. You can see the code below defines the same thing. So now we define an observation sequence. A sequence of observation is defined as a one-dimensional array. The observed data is defined as the observation sequence, which is a sequence of integers representing the corresponding observation in the observation list. So here we define the sequence of observation in a NumPy array, and we reshape it and print the output accordingly. So we predict the most likely sequence of hidden state. So the most likely sequence of hidden state is computed using the prediction method of the HMM model. Decode the observation sequence. The Viterbi algorithm is used to calculate the most likely sequence of hidden states that generated the observation using the decode method of the model. The method returns the log probability of the most likely sequence of hidden state and the sequence of the hidden state itself. You can see that we are finding the log probability, the hidden state, and we use the model decode to find all this, and then accordingly we print those out too. Lastly, we plot the result. Okay, so here we are having most likely hidden state by time step, and since we have two factors, that is sunny or rainy, we plot it accordingly, and you can see the legends do the same thing. So I hope you have obtained a brief insights on the HMM. Thank you for your valuable time. I will see you in my next video.